All right, hello everyone. It's January 12th. Right, before we start today, I have to go back to yesterday's problem. So I tried a little bit this morning, but no matter what I threw at it, it just didn't work. So eventually I had to check the solution. And the editorial has two solutions. One is using a stack, which I think is not correct. Or, I mean, it is correct, but I'm not convinced because it has this sentence. It says, if the character is a close parentheses, then we'll check if there's a match for the open first, right? If it is a matching open, then we'll pop it. So basically, what it says is if I have something like this, a left, a flexible, and a right, when I see the right, I can ignore this and I match it with this thing. Now, this is something I couldn't. I just couldn't for the life of me figure out why. I was not convinced. I'm not convinced still, because you cannot just ignore all the other flexibles in between, right? You can't just say, when I see this, I'll match with the front, and then I'll ignore everything in the middle. I don't know, like how can you do that? Like, how can you just say, like with confidence, it will always match to this one? I mean, the reality is it is not, because I can have this as a left, then you will match with this, or have this is a right, it will match with this, right? There are two ways of matching. That was the problem we had yesterday. It just didn't make sense. So eventually I did not code based on this solution. I mean, it is correct, which basically means it doesn't really matter. You can always match like however you want, but that was not how I can be convinced. So eventually, the method I use is actually very simple. It's just we do two paths, left to right, and I will check if all the locked right can be taken care of, right? So basically, we will count the right, and I will count the locked and flexible, the left and the flexible, because both can be used to balance the right. So as long as we go through S, as long as all the right can be handled, that means left to right, we're good. And we'll do the same thing from right to left and see if all the locked left can be handled. If that's also good, that just means given any stretch, right? Given any stretch, we have enough left and flexible to handle the right, and enough right and flexible to handle the left. So they will always be in balance. And since they will always be in balance, then we can always find a way to figure it out. So this, at least it makes sense to me. Okay, it makes sense to me, and I will say it's not 100%. Like I feel like there's still something missing, but overall I can accept this. Right? I can accept like left to right, everything's good. Right to left, everything's good. So it's most likely that we can find a way to deal with this. But anyway, that's how this one is solved. I mean, the solution itself is quite straightforward. It's not difficult at all. But to arrive here, it's a lot of struggle. And of course, this is also not the same as what was mentioned here, because here it used the same way, right? It says if it's right parentheses, it will first check the open brackets, which is the left, right? The left bracket first, and then check the unlocked. That's, again, I do not think this is it's not proved. I couldn't prove it. So eventually I went to the solutions and find something that I think makes more sense. So anyway, so this is this problem. Okay, now we all done and we can move on to today's problem. Minimum length of string after operation. So you're given a string S, you can perform the following process on S any number of times. Choose an index I in the string such that there is at least one character to the left of index I that is equal to Si, and at least one character to the right that is also equal to, okay? Delete the closest character to the left of index I that is equal to this, and delete on the right hand side. Return the minimum length of the final string that you can achieve. So let's go through this example. A, B, A, C, B, C, B, B, right? So choose index I such that there is at least one to the left and one to the right, and you can delete them. Delete the closest. So B, I don't have anything on the left, so if I choose this, then I'll delete this, and I'll delete this. Okay. Then I can choose this, then I'll delete this, I'll delete this. Then I choose this, I cannot choose this. So we'll end up A, C, B, C, B. That's 5. Okay, so I think it's saying by choosing different indices, you're going to have a different effect, right? Do you think that's, I mean, we don't really need to care about everybody else because we are only affecting the letters that's the same. So we can actually transform this. You know what? Let's just rewrite this. We can transform this into a different data structure, like A, right? 0, B is 1, 0, 1, 2, 3. This will be 4, 5, 6, 7, 8. Right, this is why after you transform. Then basically the question is what's the maximum you can remove? I mean, the max you can remove, if you choose something, right, it will remove the ones towards the, so, okay, let's say we have, you know, I0, I1, I2, I3, I4, okay? So if I choose this, then I'll remove this and this. Then I can choose this, I can remove this and this. If I choose the middle, yeah, if I choose this, I'll remove this. If I choose this, I'll remove this. So I only have one left. But if I choose, what are you trying to do? What I'm trying to say is I need to choose something in the middle. Because if I choose something in the middle, right, I'll remove the one on the side. So if I have additional ones, then these two can be removed as well. So it can be, you know, right, 5. If I choose the one in the middle, I'll remove these. And I can choose the one in the middle again, I'll remove these. So eventually I'll have one left. But if I don't do it, if I start from here, I mean, in this case, if I start from here, is also working, right? And you move here, then you delete. So are you saying that it's deterministic, how many you can remove? Like if I have 3, okay, if you're going 1, if I have 4, because this is the only one I can choose, I'll choose this. So I'll remove these two, and that's it, right? If I have 5, I have 1, if I have 6, 2, 3, 4, 5, 6. If I have 6, if I choose this, I'll remove these two, right? So each time you choose, I mean, yeah, it is deterministic because each time you choose, you'll remove 2, right? You choose another one, you remove 2. So now 4, we know 1 and 3. Okay, hold on. 1 will give you 1, 2 will give you 2, 3 will give you 1, 4 will give you 2, 5 will give you 1. Because 4 is 2 because you get 1, you remove 2, so you have 2, so 2 remain is 2, right? 5, you pick any one, right? So it'll be 3, so pick 1. So 6 is going to be 2 because 6 minus 2 is 4, right? And 7 is going to be 1. And 8 is going to be 2. So it's just going to be 1, 2, 1, 2, 1, 2. So this is 3. So this one will give us 1. This is 4 will give us 2. This is 2 will give us 2. So the answer is, so basically if you're even, you're 2. If you're odd, you're 1. So now we just need to do a counter. Right, we need to count how many we have. All right, so we'll first commit yesterday's. And now we're gonna copy again for today. All right, so we'll say counter 6 ooh can say C of counter if it's even it's 2, otherwise oh, that's actually not true. Depending on if C is 0, right? If C is not equal to 0, if C is not equal to 0, then we'll do this, and then we'll return rest. Okay, let's give us a shot. It's my bad. Actually, we can do some always fun. Always fun to do something like that. Yep, I think looks good. Three to do 3. First, we obtain the count, the frequency, right, of each letter. Then we realize that there is a pattern. Given one letter, after removal, we have 1. 2, we have 2. 3, we have 1. 4, 3, we remove, we pick 1, right? We pick 1 letter and remove 2, which becomes 1. We pick 1 letter and then remove 2, the remaining 2 letters produce 2. 5 minus 2 equals to 3. 3 goes to 1. 6 minus 2. 2. Odd 1. Even 2. Thus the problem becomes, thus we go through all the frequencies and add 1 if the frequency is odd, or add 2 if it is even, not event. Okay, so we're going to run this. Just do one more time, make sure that everything is fine. And let's run one more. Just make sure that everything is correct. Right, if it is, I'll submit it. This should be 0 millisecond or 1 millisecond. 11. Oh, because we have a counter, that's why. 117702. Okay, not bad. 11 milliseconds, 7702 percentile. Alright, editorial should be about the same. Yep. It's about right. Frequency array is exactly the same. Okay, that's not a tough problem. All right, we have some time, or maybe we do not. I mean, I need to train. How about we just look at this problem and then we'll ruminate on it. So you're given an array of integers. Your task is to find the length of the longest subsequence such that the absolute difference between consecutive elements form a non-increasing sequence of integers. In other words, for a subsequence this, then the absolute difference must form a non-increasing between the length of such a subsequence. So we want the longest, right? Subsequence such that the absolute difference between them is always decreasing. Is not increasing. It could be equal. So in this case, the second one, this is 1. So kind of very limiting. So you want it to be as big as possible to begin with. Naturally, because you can actually go up, right? So these are 3. And the maximum is, this is 1. So this is also 1. So this is, so you get 1 and you get 1. Huh. Maybe DP, because I mean the reason is I saw the constraints. These constraints kind of signify maybe some DP issue, some DP stuff, you know. I don't know. So could be, you know, DPIJ, right? So up until, I can say, the longest subsequence from 0 to nums0 to nums I, right? But how does that help, right? How does that help? So if I have the longest, like say of a previous, I know from the start to any one of them, the longest subsequence. The length, right? We only know the length. And when you are in, or is the DP like including? I shouldn't say including. It should just be from the start to an index. And we have the longest subsequence. And that point, we can say, we need to know what's the last, don't we? That's actually not. Or the difference, right? Or the difference. We can say the longest subsequence in range 0 to I, okay, in range 0 to I, with the last absolute difference at some value, okay? And then the difference could be from 0 all the way to 299, right? So 0 to 299. So once we have that, yeah, let's just call it, right? We can call it DPIJ. Okay, DPIJ is the length, okay, of the longest subsequence in range nums from 0 to I, well, I plus 1 using Python's syntax with the final, the last difference, the last pair, and the last pair, we just call the last absolute difference, right? The last absolute difference equal to j. Okay, so with that, we need to compute dp, I plus 1. Basically, dp I plus 1 starting from 0 all the way to 299, right? We need to go through all of them. So if I want to compute dp I plus 1, 0, right? What do I do? So I know the previous, I can go, that's the thing. That is the thing. If you just say including, that's not gonna work. I feel like it has to be from ending, okay, ending at nums I, right? Ending at it. It has to end at this. But if you do ending at this, now we say ending at the I plus 1, right? Ending at here, then you have to go through every single one before. And that's something I don't want to do, because that will turn into n squared. Right? I don't want to go every single one, because I'm ending at a certain point. Because we don't know what is included in the subsequence, right? We don't know what is included in the subsequence. I mean, we can know the last difference, right? I know the last difference. So because it's non-increasing, so based on the last difference, like if the last difference is 0, then I have to be 0 as well. But I don't know what the last one is. Hey, how are we going to do that? How are we going to do that? Let me think. Or ending at some, I don't know, ending at. Maybe I want to use some simple. Yeah, like this one, 10, 20, 10, 19, 10, and 20, right? We say a given 2 is always going to be 2, right? So now, what if I want to compute this position, right? I want to compute this. I know the maximum of the previous. I knew it. So I need to know the maximum here. So the question is, do I include this, right? I want to know if I include this, can I make it longer? So I need to know in the previous, what is the ending, right? What is the ending? I do have to know what is the ending. I can say the index, the end index. Okay, it ends at certain index. So now, from me, I can check. Well, it's not just the ending. It also need to be, oh Lord, it has to be the ending, and I also need to know the difference. All right. So in this case, I say the previous ending at 20, and the difference, absolute difference, is 10. And now you just compare yourself to the previous ending, and the difference is 10 is the same. So you say I can extend it, right? I can extend it. And next one, you can extend. Next one, you can extend. Now here, right? So basically, if we go through the whole thing, now we're looking at this one. So this one, you're looking at the previous. You say the ending is at the 10, at this 10, right? With the difference being 9. And now you're at 20, so it doesn't work, right? Because the difference is 10. So you need to find the difference is 9. So you need to go to see the previous thing that will end at 20 minus 9 or 20 plus 9, right? So it has to be 11 smaller or equal to 11 or larger or equal to 29. It has to be that. And then I'm thinking you're what, binary search this? But there's no binary search, right? Because it's not sorted. So you need to find the latest occurrence of something smaller or equal to 11. The latest occurrence of something smaller or equal to 11. Huh. We can search. It takes only 300. So you search from 11 down. You search from 11 down to 1. Let's say we keep an array, calling it latest index. Okay, I have 1, 2, all the way to 300. This tells you what is the latest index of 1. Latest index is 2, right? So in this case, I go 11 doesn't exist, and then I go to 10. The latest existence of 10 is index 0, 1, 2, right? Index 2. So I know the latest of 10 is index 2. Then I go to the DP table because DP2, right? DP2, which means it ends at 2. Okay, it has to take 2. It has to take 2. Yeah, it has to take 2. That is 3. The length is 3. So I say for me, then it will become 4, right? And that this will become 4. But and larger than 21, there's nothing larger than 21, right? And I can actually do this by going through this once to get the maximum value. And then the overall is 5. So it should be 5. Okay, yeah, I think that is a solution. That will be OMN, where M is the max of nums and N is len nums. We might even be able to just quickly get this one up, but gotta train, so we'll deal with this tomorrow. We have an idea, we'll see how it goes tomorrow. I'll see you guys tomorrow.